In this section on TensorFlow Basics, we shall see how TensorFlow will be used to build models and train using automatic differentiation. Before getting to that, let's take this simple example. Recall this example we already had. So we have g of x equals log of x plus sigmoid of x squared minus e to the power of tanh of x. Now from this we could build this computational graph where b is equals to the log of x, so b is the log of this, c is x squared, d is the sigmoid of c, e is tanh of x, f is exponential of e, and finally g, this is equals b plus d minus f, and this corresponds to this. Now we shall calculate the partial derivative of g with respect to x. And we have the formula derivative of g with respect to xi, that's any of these values, is equal to sum of that derivative with respect to xj times the derivative of xj with respect to xi. Now concretely, we have here the partial or the derivative of g with respect to x is the derivative of g with respect to b times derivative of b with respect to x plus, so basically we're getting this from here, so we are finding dg with respect to x, dg with respect to b plus dg with respect to d minus dg with respect to f, and then dg with respect to b is this, dg with respect to d is dg with respect to d times dd with respect to x, and then df or dg with respect to f is dg with respect to f times df with respect to x. We had seen this already. Now we should also note that we are simply applying this formula, as this formula goes that to find the derivative of any of this with respect to one other point, we simply sum the derivatives of say g with respect to any point which helps link, in this case, x to g. So that's why in this case we pass through b, we pass through d, we pass through f. And then to find the derivative of d with respect to x, that is this d with respect to x, the only point which is actually linking x and d is just c. So that's why in this case we don't really have a sum, we just have dd on dc times dc on dx. So there we go. And then to find the derivative of f with respect to x, we have df on de times de on dx. Now concretely, we have dg on db, which is 1, dg on dd, which is 1, dg on df, which is 1, db on dx, which is 1 on x, because the derivative of the log function is 1 on x. dd on de is d into 1 minus d. Recall that we are seeing here, when you derive the sigmoid function, is simply y times 1 minus y. In this case, our y is d. So we have d into 1 minus d. So it's actually sigmoid into 1 minus sigmoid. And since sigmoid of c is d, we just maintain here d. And then we have dc on dx, which is 2x. That's very easy to see. df on de, which is f. So because the derivative of exponential of x, for example, in this case, remains the same, so we have the df on de, which is f, and then de on dx, which is 1 minus e squared. Recall the derivative of tanh is 1 minus tanh squared. Now suppose we pass into this graph the value x equals 2. So suppose we put in 2 here. We want to know, given x equals 2, this derivative with respect, or the derivative of g with respect to x. So db on dx, which is a half, that's from here since x is 2, dd on de, which is a sigmoid of 4, because here we're having the sigmoid of c, since d is a sigmoid of c, but c is equals x squared and x is 2, so x squared is 4, so c is 4, so we have the sigmoid of 4 into 1 minus sigmoid of 4. And then dc on dx, which is equals 4, since we have 2 times 2, df on de, exponential of tanh of 2, de on dx, 1 minus tanh of 2 square, and all of this is because e is equals, or rather x equals 2, and since e is tanh 2, we have exponential of tanh 2. So that's it here. Then replacing all these values, we have that dg on dx is equals 0.385. So let's calculate this quickly on TensorFlow to see exactly how we get this value. So to make use of TensorFlow and its functions, we have to import TensorFlow as TF, run this, and then we have this variable x, which takes in 0.5. This is 1 on 2, as we just saw in the slides, 4 times this, into 1 minus this, minus all this. So basically, this is what we just had in the slide. We're running this. We'll see how we obtain 0.385. Okay, there we go. We have the value as expected. Now you notice that this value x is of type tf.tensor. So this brings us to the most common data type in TensorFlow, hence the name TensorFlow, because we're basically dealing with tensors, which are n-dimensional arrays. So we've just been given a simple equation, and then we've gone by hand and solved it when x equals 2 to find the derivative of g with respect to x. In this case, also we could put here, this is actually dg with respect to x. So that's it. So we have dg with respect to x. Now let's see how with TensorFlow we could automate this, so we don't need necessarily to always derive it and then come maybe and put the final answer this way to obtain the partial derivative of whatever part of the graph with respect to another, or rather whatever node with respect to another node. So say we have this, so we've defined this a as a constant. So note that we have here tf.constant. This is basically a tensor, so if we print this out, we have tf.constant 2.0. Run this again, you see you still have this tf.tensor we had seen above. And as you can see, this is a constant tensor. So let's modify this and put this a variable. So we have this variable. So here we have this variable. Running this. Now instead of tf.tensor as we had when we had the constant, we have a tf.variable. For now, let's just run this code and see what it gives us as output. So here we're told this is not defined. We put this tf.sigmoid. There we go. Run this. We'll notice that we have the same answer we had just above. And if you look very carefully, you'll see that this b equals this, c equals this, d, e, f, and then finally g is exactly the same graph we had just built in the slides. So using TensorFlow, we could automatically calculate the gradient of g with respect to a. Now note that a is actually equals x, so you could take this for uniformity, but let's take that away. Then we could run this to see its output. We have exactly the same answer we had just above, but with the difference that all we needed to do here was simply to define this computational graph. And with TensorFlow, once you define it just like this, you could automatically calculate the derivative of one of the nodes with respect to another. Now let's try to understand the syntax. In order for us to keep track of the different gradients which make up our graph, we use this with tf.gradient_tape as tape. And the word tape comes from record. So basically we are recording the gradients as we build in the graph. So in this case, as you build the graph, we keep on recording gradients like db with respect to x, dc with respect to x, dd with respect to c, dc with respect to x. Anyway, dd with respect to c will obviously give us dd with respect to x once we have dc with respect to x. Then we have de with respect to x, df with respect to e, dg with respect to f, dg with respect to d, dg with respect to b. So basically what we're doing is we're just moving through the graph and recording or taping all the gradients. And once this is done, we could calculate using that tape the gradient of any of these nodes or any of these values with respect to another value on another node. So now we've understood this first line. We now look at tape.watch. So we have defined this as tape. So basically this is tf.gradient tape. So tf.gradient tape.watch a. Now because a is a simple tensor, we have to watch it. To watch means we have to keep track of the different gradients which may be related to A. So if we take away this, you'll have a different answer. Let's take this line away. So we have here known, because that taping or recording wasn't done. So that's why it's important for us to always make sure we watch, or we always keep track of A. Once that is done, we can simply define a graph, and then later on, outside of this width, as we print out the gradient of any of these with respect to the other. So we could, for example, here print out the gradient of C with respect to A, and since C is equals A squared, we should normally have 2A, and A is equals 2, so we should normally have 4. So if we run this, we should have 4, and there we go. That's exactly what we have. Also, if we were working with variables, that is, if we were just having variables instead of constants or instead of tensors, tf.variable this, and then you run this, you see you have this, but even when you take this off, you'll still have 4. So the difference here is with variables, we don't need to keep track. So automatically variables gradients are being tracked when you are in this tf gradient tape. Now, a question you may be asking yourself is, what if you are having to deal with a function which TensorFlow doesn't have already? So suppose we have a function sig. So suppose sigmoid wasn't defined in TensorFlow. Then we shall use this tf.custom gradient decorator, which is provided to us by TensorFlow. We define the function. So in this case, since we have the sigmoid function, we have 1 divided by 1 plus e to the negative x, and then we define the gradient. So this gradient will permit us, for example, calculate the derivative of, say, g with respect to a, and that's simply because we have the derivative of d with respect to c, since we've defined it as such. Now, since here we have d, this will mean we should be having the derivative of, here we should be having d. So this is gonna give us something like this, d. Now it doesn't matter, yeah. So we have this. Now this is kind of like a template. So we could say we have function definition, and then dy times gradient definition. Okay, so in general, when you have a function which you want to build, which doesn't come ready with TensorFlow, you could build this function and then define this custom gradient, such that simply it could be added onto a computational graph. So let's take some steps back. We run this, and there we go. See here that we have this right answer. So this practically behaves same as if we had this tf.sigmoid right here. Now let's take off, put here 1. Yeah, we have this. We see that we have a wrong answer. So let's take this back, and there we go. So this shows us that with TensorFlow, once we have a function and we're able to calculate this gradient by hand, we could automatically add it on to a computational graph just by following this simple template. We shall then look at different tensors. Let's start with this rank 0 tensor, which is basically this value 1. It could be a value like, say, 23 or whatever value. Also, defining this in TensorFlow is quite easy. We just have x rank 0 equals tf.constant. So we have tf.constant 1.0. There we go. We could print this out. So we'll print this x rank 0. We see that we have this tensor of type float32, and it actually has no shape, or this shape tuple is empty. And then the next tensor we'll be looking at is this tensor of shape 3, which can be seen as a vector that takes three different values, 2, 0, -3. Defining this in TensorFlow, copy here, put this out, run it, and we have this R tensor. This time around we have an integer, and then followed by this tensor of rank 2, which happens to be a 4 by 3 dimensional matrix. Here we have 4 rows, 1, 2, 3, 4, and 3 columns, 1, 2, 3. Now taking this to TensorFlow, this is what we get. We run it. We have this tensor of data type float32, shape 4, 3, telling us that we have 4 rows and 3 columns. And if we take this off like this, we see that we now have integers. Now suppose we've packed in several of these matrices or several of these rank 2 tensors together. So in this case, we've packed 4 different 2 by 3 rank 2 tensors together. Now how do we see this 2 by 3? We have 1, 2, and then 1, 2, 3 columns, 1, 2, 1, 2, 3 columns. You could check on our complete linear algebra course in case you don't understand all this. So we have this, and then we have 1, 2, 3, 4. So we could picture it out this way. So we have 1, which is this, 2, this, 3, this, 4, that. So we have 1, 2, 3, 4, and then 1, 2, 1, 2, 3. So it is a 4, 2, or the shape rather is 4 by 2 by 3. Then doing this in TensorFlow, we have this x, so we'll change this to x rank 3. Here we have x rank 3. So if you look carefully, we have this first matrix, we have the next, we have this, and finally we have this. So let's run this, and there we go. This is a rank 3 tensor. We have shape 4, 2, 3, data type float, for obvious reasons. Now the reason we're looking at all these different tensor types is because the kind of data we'll be working with wouldn't just be, for example, just this TF the constant 2.0 or just rank 0 tensor. Say we're working with image data, generally they take this form, as we have a width, a height, and then a number of channels, which generally are 3. So already this represents an image which is of dimension 4 by 2 and with 3 channels, and these 3 channels could represent the G, and then the B, which stand for red, green, and blue channels. It's also important to note that in some formatting, you could, instead of having 4 to 3 to represent the width, height, and then the number of channels, you could instead have number of channels, comma, width, comma, height. So sometimes on some other libraries we could work this way. So we could have number of channels, width, and height. So in that case, we'll be having 3, 4, 2 instead of 4, 2, 3. But generally with TensorFlow, we shall work this way. So it's already very important for you to be able to play around with these tensors. Now let's look at tensor of rank 4. Now before looking at tensor of rank 4, we shall look at 2 other tensors of rank 3, because the tensor of rank 4 is gotten by stacking up this tensor of rank 3. So we have defined this tensor of rank 3, this other tensor of rank 3, this other one of rank 3, and then finally we have this tensor of rank 4, which is gotten by stacking up these other tensors. So if you look at this carefully, we have this one, which is this, next, which is this, and finally this. So when we stack these tensors up, or just rank 3 tensors up, we form a rank 4 tensor, which is simply going to be of shape 1, 2, 3, so 3, and then 1, 2, 3, 4, 4. So we have 3, we have 4, and then we have 1, 2, 2, and then 1, 2, 3, 3. So we have 3, which is this, 4, 2, and then 3. So in TensorFlow, this is what it looks like. We have this 1, 2, 3. So these are the rank 3 tensors which have been stacked up to form this rank 4 tensor. So yeah, we could define this rank 4, print out this rank 4 tensor, and this is our results. So we have shape 3, 4, 2, 3. Now clearly one application of working with this kind of tensors is when you're dealing with many images. So as in here, we just trying to code one image or trying to pass one image into our model, for example. Now what if we're working with many more images? So like in this case, we're supposing we're working with 3 images. So we have the first image which is going to be 4, 2, 3, as we could have here, the next image this, and the next image that. So we'll see clearly how important it is for us to be able to play around with those tensors. Other basic things you could do with tensors, you could get your shape by simply doing x. Say we could print out x, rank 0 dot shape. So we have this 1, 2, 3. We have rank 3 now defined. Let's run this. So that's rank 3, then rank 4. We can also find their data type. So we have this .d type, and then the number of dimensions, enzyme. So here we have 4 different dimensions. Could get the size. So we have tf.size, tf.size of this. We obtain 72, since 3 times 4 times 2 times 3 is 72. We could also reshape this. So reshape, then we give it the shape. So we could take, say for example, 3, -1. So right here we have this answer. We have this shape 324, because since we put in -1 right here, we're simply telling TensorFlow that this first dimension should be 3, and then the next should automatically be calculated. And since we have 3, 4, 2, 3, this remaining tensors which have dimension or shape 4, 2, 3 have been squashed into 3 different 24 dimension vectors. So if we look back here, we had this 1, 2, 3, 4 by 2 by 3 tensors. Now for each of this, we just take all these values and then form this 24 dimension vector. So we have 2, 1, 9, 4, -3, 32, right up to 3, 5, -1, and that's exactly what we have here. So this up to this is for this first tensor, and then the next from 387 to 32 right up to 531 is this next, and then finally this is represented by this. So that's how TF the reshape works. Now let's play around with this. Let's modify this. Say we have instead 4, so we're taking this the next 4, and then for the next we're saying 6. So we'll run this again, and we have this. So now the first 2 dimensions, that's 3 and 4, are maintained. We have 3, 4, 3, 4, and then this last 2, 2, 3 squashed into this 6. So that's why here we have this 3 by 4 by 6 dimension tensor. And then if we modify this, instead of putting 6, suppose we put 5, we find out we have an error. Input to reshape is a tensor with 72 values, but the requested shape has only 60 values. So when doing reshape, it has to be such that the number of values we are working with actually are the same. So let's send this back to 6, or even just -1. And obviously TensorFlow will select the value 6 for us automatically, since we've said we want this to be done. Now there are also some wrong transformations in which we could say, for example, instead of 3 4, we'll take this to 4 3. We'll do this. We'll find that it's going to work because we still have the same number of elements, but this happens to be a wrong transformation. So generally, interchanging the positions of dimensions like this, that's taking this 3 4, interchanging this like this, isn't a very good idea. Given that sometimes we work with numpy arrays, it's important we know how to convert from a tensor to a numpy array and vice versa. So say we have a tensor like x rank 0. To obtain the numpy array, we simply have x rank 0 dot numpy. So that's it. Now let's take this off and you can see the difference. So there we go. We send this back. This is a numpy array. Now if we want to convert this to a tensor, we just simply have tf dot convert to tensor. Then we have our numpy array, or rather we have our TensorFlow tensor. So before going ahead, you have to take up this in-class exercise. For our in-class exercise, you have to come to TensorFlow API page. This is it. Come right where we have this functions. So where we have these functions, you have to go through each and every one of these functions and understand how it works. So like we could go through this right up to the very last one. So let's take, for example, this where. So this is tf.where. What you do is simply click on this, then you try to understand how it works. You try to take a simple example before moving ahead. So make sure you understand each and every one of these before going ahead. Now that's it for the first part of this in-class exercise. For the next part, you have to come to this tf.math and then do same. So you have to come to tf.math and make sure you understand each and every one of these functions. So that's it for the in-class exercise. Make sure you do it before continuing so that when you're building projects with TensorFlow, you find it easy making use of these functions to speed up your code and then come up with the best models possible.